Okay, in the discussion of conservation of charge, in this slide we try to derive the Gauss's law of electrical field in terms of the conservation of charge and Ampere's Kirchhoff law. The three equations are listed below, as you can see here. So in example 2.5, we have set up as illustrated in the figure. Here in the origin of the coordinate system, we have a point charge, say Q. And as you can see here, Q is labeled as a function of time, so it's written as Qt, placed at the center of the origin. And there is a constant current flow flowing out of the point charge Q as I. And this current I is a constant current flowing in the positive z direction. So as you can see here, there is electrical current flowing out of the origin. So as you can expect it, the number of charge Q should decreases as the time goes. And in the neighborhood of this scenario, we have a hemispherical surface. This is the top hemispherical surface as shown in the figure. And there is a planar surface, a planar circular surface lying on the xy plane. So this planar xy, this planar circular surface happens to cut the point charge Q in half. Okay, cut in the middle of the point charge. And of course, you can argue that, well, it's a point charge, how do you cut it in half? Well, anyway, from the engineering perspective, well, that's the problem set up. So we have an observation surface, the top hemispherical surface and the bottom planar surface. So the two surfaces forms a closed surface, okay? And in this neighborhood, we see that Q becomes smaller and smaller as the time goes because there is a constant current flow I flowing out of this region in the positive z direction. So how do we describe the scenario in terms of Maxwell equation? So in this slide, we first apply the Ampere's Kirchhoff law. That is, to the left of the equation mark is a closed loop integral of a magnetic field. So we can describe the magnetic field along a specific contour. Now, along a specific closed contour C, that is the contour, the circular contour C on the xy plane. Okay, so to the left of equation 2.32, essentially describe the closed loop integral of a magnetic field intensity along this circular path. All right? And the closed loop integral on this circular path represents what? Represents that any surface which can be this S, hemispherical surface on the top. And what is the physical interpretation of this? That is the total current passing through, well, actually, to be more specific, is the current flowing upward out of this hemispherical surface, including the actual current I and the equivalent current, the equivalent displacement current, which can be expressed as the time derivative of displacement flux, the surface integral of displacement flux on this hemispherical surface S. Okay, so this is the basing on the Amperse-Acoustical law, we can write up this equation. And from the Gauss's law for the electrical field, to record the Gauss's law for the electrical field, let's go back a little bit. This is the Gauss's law of electrical field. Supposing that you have a closed surface, then the total displacement flux flowing out of this closed surface shall equal to the number of the total charge enclosed within this closed surface. So if we apply the Gauss's law for the electrical field, then in this scenario, we can write up this relationship. Well, this relationship actually comes from the fact that if we write the closed loop integral, closed surface integral of D in this region, say that we have not only the upper hemisphere, and we also have a bottom hemisphere. Then this total sphere, because the point charge Q is enclosed within this total sphere, this spherical surface, then the surface integral of this spherical surface on displacement flux D shall give you the total charge enclosing within this region, that will be Q. And if you cut this spherical surface in half, then the amount of charge enclosed on the upper half, so you can think of this problem as if you only count half of the spherical integration, that is only the upper half of this region, then the result will be what? Will be half of the charge enclosed in this region. Of course, this result is the same if S is replaced by H prime, which is the lower half of the lower hemisphere, bottom hemisphere, the lower half of the spherical surface will also give you Q over 2, half of the charge within this region. Okay, so as you can see here, due to the symmetry in the problem geometry, half of the electrical flux flowing out of the top hemisphere, half of the electrical flux flowing past through the bottom hemisphere. And this can be related to the distribution of the charge. Half of the charge is located on the top hemisphere, and the other half is located within the bottom hemisphere. All right, by applying this relationship and place it back to the original Amperse-Acoustical law, the equation can be, well, this is this is what we just discussed, all right? So the spherical surface integral of D on the bottom half equals to Q over 2, and the top hemisphere is Q over 2 as well. And if you apply this relationship to the Ampere-Secchio law, it shall give you this relationship, okay? Why? Because on the bottom half, to produce outgoing flux direction that is passing out of the spherical surface, the contour direction should be determined in this way. C prime direction happens to be the opposite of C direction of the original contour. So as you can see here, the C direction is counterclockwise, while C prime is in the opposite direction, which is clockwise from your perspective. So it will produce positive going flux this way, passing through the bottom hemisphere. So if you do a closed loop integral of the magnetic field intensity H on C prime, it shall equivalent to what? Equivalent to actual current I plus the displacement current, like this term. And as we know from the description of the problem, there is no actual current passing through the bottom hemisphere. We only have I going up and nothing going down. So the first term of Ampere-Secchio law here is 0. You have no actual current flowing out of the bottom hemisphere. And if you look at the displacement flux, the displacement current, that is the time derivative of the surface integral of D, you got this thing, which is minus I over 2, because what? Because according to the conservation of charge, the total currents flowing out of this complete spherical surface, that is the surface integral of J, is what? Equals to I. The actual currents flowing out of this region equals to the time derivative of D over this. All right. Nah. So this is the conservation of charge. So that should be written as okay. All right. So as you can see from here, half of the what should I do? So the total current I is equivalent to the negative of decrease of Q over T. So dq over dt, and taking the minus of that is the total currents flowing out of this region. And because the thing equals to q over 2, so by substituting equation 2.34 into this equation, you can replace it with minus I over 2, which means what? Which means in this problem, we have actual currents I flowing upward along the positive z direction. And this actual current I is replaced with influx of displacement current. And due to the symmetry of the geometry, half of the displacement currents flows in comes from the top hemisphere, and the other half comes in from the bottom hemisphere. And because their direction are flows in, so you have a negative sign over here. So you have minus I over 2. 好，再讲一次哈，这边这个题目的状况是什么？你在坐标系统中心 在坐标系统中心有一个 Q， 随着时间越来越少，而它根据 conservation of charge 可以看出来 Q 的减少的时间 time rate of Q of decrease equals to I 哈 ，I 等于 minus dq dt 嘛哈，这是根据 conservation of charge。那这一个 Q 的减少对应到的是 D 的变化 ，D 的面积分的变化哈。那因为是对称摆放的，所以上半的球面跟下半的球面各吃进来2/Q 的，它的那个 D 的 surface integral 会各取一半啦哈，所以上半部是2/Q， 下半部也是2/Q。所以，假如你把这个关系带入安培电路定律啊，从下半部平面来看的话，它只有 displacement current， 没有真实电流，所以它的磁场的封闭回路线积分会等于这个 D 的实变率，所以会等于根据上面这几个式子看起来，它等于-2/I。OK 啊，那上半部呢？上半部它也会有这个-2/I， 也就是以 displacement current 的形式补充进来的电流，等效电流，以及什么？以 I 的大小往外流出去的真实电流。好，所以你在看到下一页的时候，就会看到 ，so for the top hemisphere, if you take in the closed loop integral of the magnetic field intensity H on the original contour C, it can be regarded as the sum of actual current and the displacement current. The amount of actual current is I. What is the amount of displacement current? Minus I over 2, minus I over 2, as we can see from the previous slide. So the total result of the closed loop integral of magnetic field on the top hemisphere is I over 2. And if you combine the two, you will end up with 0. Why? Because C and C prime are of the same contour, of opposite direction. So the sum of the two should equals to 0. Also, the total currents, including the actual currents and the displacement current flowing out of closed surface should be 0 at all time. So the currents flowing out of the top surface is I over 2. The total current flowing out of the bottom surface is minus I over 2. So the summation of the two is 0 as well. So that shall give you a consistent solution for this problem scenario. Okay, so for any region with time varying charge density and currents, the total currents passing through this region will be 0 at all time. Okay. So here we have, if you combine the bottom surface, that will enclose the charge Q entirely, and the total currents passing through this closed surface shall be 0 at all time. All right, so if we try to illustrate the problem in terms of a graph, you can see as this figure says, and here in this region, because the charge is decreasing as the time goes, and it turns out to be actual currents I flowing out of the surface. And for this region, for the neighborhood, there shall be a displacement current to compensate the actual current that is leaving the space. 所以在这个空间里头，总电流量必须要是连续的，也就是你有 I 出去，就必须有 I 补进来。那这个补进来的 I 是以什么样的形式？是以 displacement current 的形式。那因为你的电流的来源是这个持续减少的点电荷，所以既然这个点电荷在这里是一个几何的对称中心，所以它所导致的电场，它所导致的电通量密度也是均匀分布的，所以有一半的 displacement current 位移电流是从上半部补进来，有一半的 displacement current 是从下半部补进来，而这些 displacement 的 current 的总量会是多少？会是 I 嘛，等于从这个空间离开的那个真实电流 I。所以上半部补进来的是负的2/2 I， 下半部补进来的也是负2/2 I， 所以总体加起来还是等于0，还是等于0 ，OK， 那你说这个事情可不可以一路持续下去？当然不行了当你这边的 Q 完全没有的时候，就怎样？就没有这个 I 无以为继那这个。没有这个 I 流出去，那也没有这个 displacement current I 流进来去补充它就不会有。但是在这个时候，在这个当下，也就是还有 Q 在这个原点的时候，那只要这个 Q 持续减少，那么实际流出去的真实电流 I 跟它补充进来的 displacement current I 是一个对一样大小的关系那只是从这个题目来看的话，你可以看到一半是从上面补进来，一半从下面补进来 ，OK？ Alright, so let's move on to section 2.7. Here we will discuss the special case of a static field. 进场的状况底下。So here are the 4+1 Maxwell equation, including the Faraday's law and Persecution law, Gauss's law for the electrical field, and Gauss's law for the magnetic field, and the law of conservation of charge. So here you can see to the left, 等到左边 to the left are integral, spatial integral, 空间的积分，有没有看到？注意到这个式子。等号左边都是空间的积分 ，they include two closed loop integral, two line integral, and three closed surface integral. Three closed surface integral. And to the right, there are a couple of things. There are two things that you need to notice. This is the surface integral of J and the bottom integral of rho. What is their what are their implications? They are the so-called sources for the electromagnetic field, electromagnetic wave. 电磁波或者说电磁场的能量的来源来自于 J 跟 Low。当你取了面积分或者取了体积分之后，它出来的就是 I 跟 Q。所以电流是磁场的直接来源 ，Q 嘞，电荷嘞是电场的直接来源。所以在这一组式子里头，你要留意到的一个式子，除了我刚刚讲的左边是空间的积分以外，包含线路的积分，还有面的积分。右边呢有两个是电磁场的来源，电流跟电荷。And there are three derivatives. One is the time derivative. There are three time derivatives on the right-hand side. They are the time derivative of magnetic flux density, time derivative of electrical flux density, and the time derivative of electrical charge. And now we are talking about, in section 2.7, we are talking about the static field, which means that we are talking about the special condition, special case of Maxwell equation under the consideration that there is no time variance, there is no time variables in this equation. So to put it simply, that is, you can leave out the terms associated with time derivatives. That is, you can set time derivative of B as 0, the time derivative of D as 0, and the time derivative of low as 0. So you can go into the static field case 进场的条件了所以在进场的状况底下，你的电磁场或者是电荷源的变化、电流源的变化没有时间变动的成分，所以你可以把原来的 Maxwell equation 里头跟时间微分有关系的项都拿掉，所以你就得到了就是这边所看到的5条式子所以这是在进场条件底下的 Maxwell equation。So here we can see some familiar relationship as we seen from electric circuits. 我们在电路学里头其实都有教过这些东西了So first thing first, that is the closed loop integral of E equals to 0. What is this? The line integral of electrical field intensity is what? Is the electrical potential, is the electrical voltage. So this, to put it simply, is that in electrical circuit theory, if you move along the circuit as a closed path, the total voltage difference will be what? Will be 0. And this relationship is referred to as the Kirchhoff voltage law. 中文叫什么我已经忘记了 KVL 嘛Kirchhoff voltage law, alright so that is, if you follows the electrical circuit in a closed path, you will observe no voltage difference. That is valid for the steady field, KVL. You also see that the total current flowing out of a node is 0. That is referred to as the Norton theory, right? Or KCL, Kirchhoff circuit law. So this equation can be described as for a specific node 在电路上的某一个节点，它进出的电流总量为0And equation 37A and B says that electrical currents produce magnetic field. Electrical charge produce electrical field. And there are no interdependence between the two equations. So here is an important observation for steady field. Under the consideration of steady field, electrical field and magnetic field are independent. Unlike the time variant case, That is, the electric and magnetic field are interdependent. Under the condition of steady field, electric and magnetic field are independent. 好了，刚刚绕口令再重述一遍了哈。在进场的状况底下，电场跟磁场是独立存在的，因为你看到这两个式子里头，磁场的归磁场，电流产生磁场；电场的归电场，电荷产生电场。所以磁场跟电荷无关，那电场也跟电流无关。为什么？因为它们都没有时变率，都没有随时间变化。所以在进场的状况底下，电场跟磁场是独立存在的。就像我以前讲过的一个例子你把虽然金属屏蔽作用能够阻挡电场，金属屏蔽作用所阻挡的电场是包括静电场还有时变电场。但是你把一个指南针关在一个金属的饼干盒里头，那个指南针还是指着北方或者是南方。为什么？因为它所感应的是地球磁场，跟电场无关。跟电场无关。金属盒子只是挡电场，它没有挡磁场。但反过来，你只要把手机放到金属笔杆盒的话，大部分情况下，那个金属盒配得够密制的话，够紧密的话，你的手机就收不到讯号，因为金属盒把电场掐死的同时，也把磁场掐死所以你的手机是收不到电磁波的讯号Alright, and the equation 2.37d is the same as the previous case. That is, the net magnetic flux passing through a closed surface always equals to 0. Alright? So here are the observations made from the Maxwell equation under steady field consideration. That is, for the steady field, for the steady field consideration, the steady electrical field is independent with the magnetic field. And steady electrical field is a conservative field, 保守场 steady electrical field is a conservative field. Why? Because in this equation, we see that the closed loop integral of E is independent of the path. So no matter what closed path it is, as long as the observation point can be moved back to the origin of the original point under static electrical field, the total electrical potential difference is 0 for all cases, for all paths. So the steady electrical field can be claimed to be a conservative field. And similarly, the magnetic flux is the same through all surfaces bounded by a closed path. That is concluding from the fourth equation. And the second and the third equation tells us electrical field is produced by electrical charge, magnetic field is produced by electrical current, and there are no interdependence between electrical field and the magnetic field. So you can say that the electrical field and magnetic field are independent under the steady field condition. And we can easily identify that the source for magnetic field is electrical current and the source for electrical field is the electrical charge. And in addition, in the case of Ampere's sequential law, the currents on the right side must be uniquely given for a given closed path C. That is, we see that because there is no displaced current involved, so the Ampere's sequential law is reduced from 3 terms into 2 terms. The left term is the closed loop integral of magnetic field, and the right term is what? Right term tells you that the closed loop integral of magnetic field H along a closed path equals to what? Equals to the current, total current passing through this region. use this relationship in following examples. 所以我们等一下会看到一些相关的 example. And a further observation from this result is that if you form a closed loop, then under the static field assumption, the total current leaving or entering this closed surface must equal to 0. So it's equivalently to what we have in the electrical circuit theory, is that the Newton theory. For a node on the circuit, the total current entering and leaving this node shall be 0 at all time. All right. So here is the illustration for this example. Suppose we have in this figure, you see two cases. You have a closed surface forming with two shell-like hemisphere surfaces, and they are all bounded by this contour C. So this shell and this shell, the other shell, forms a closed surface. And the difference is on the top is an infinitely long line, 一个无限长的电流线从左到右无限长的电流线。在进场的状况底下，有多少的电流从左边进来，就从多少电流从右边出去。所以在上面的 case 里头不会有电荷累积所以上面的话是确实的 steady field， 确实的进场所以它的净电流为0它的 net current is 0。On the other hand, for the bottom case, for the bottom plot, you have a finite conducting wire that ends up within this region. Then as the current I goes, what happens? There will be charge, electrical charge, accumulate within this region. So the bottom case cannot be a steady field case because you will accumulate electrical charge in this case. And the increasing electrical charge will continue the currents in terms of what? In terms of displacement current flowing out of this space. All right? So, if you only look at the actual currents, for this case, the closed surface integral of the actual current is non-zero. However, for the static field, the actual current enclosing with this closed surface is 0 at all time for static field. Alright, so here are some further explanation for the bottom cases. So we see that because the net currents into this closed surface is non-zero, so you will accumulate charges, and these time-varying charges will produce electrical field, time-varying electrical field. So it's not a static field case. It does not fall into the case of static field. And what happens with the accumulated charge? So as I already mentioned, the accumulated charge within this point, at this point, will continue the current in terms of displacement current. All right. So, in other words, the total currents, including actual current and displacement current, will be 0 for our closed surface for both static and time-varying field. Difference is for static field, because for static field case, because you have no displacement current, so the total currents, the zero total currents enclosing in a closed surface can be only expressed in terms of I, or J, that is the actual currents. On the other hand, for the time variant case, the currents can be either actual current J or I and the displacement current, and the displacement current. So 不管是进场或者是实变场，一个区域里头的总电流一定为零，进出的总电流一定为零。只在进场的状况底下，这个总电流只能包含真实电流，也就是 I 或 J 而在实变场的状况底下，这一个电流除了有真实的电流 I 以外，也可以是位移电流就是实变电场的部分所形成但是对于一个区域来讲，不管是实变场或者静电场，它进出的有效的总电流，包含正时电流跟位移电流，一定是零。OK， 好，所以简单讲了，就电流一定要绕一圈啦，没有那个电流是没有头尾的，它一定要绕一圈。OK， 好。Alright, then we will, for the rest of section 2.7, we will demonstrate the power of Maxwell equation using 3 examples. First example, example 2.6, asks you to calculate the electrical field due to an infinitely long line charge. This example has already been seen in section 1.5. Recall that in chapter 1, we calculate the total electrical field distribution for an infinitely long line charge based on what concept? Based on the concept of Coulomb's law. That is, we divide a very long line into a small section of point charge. We calculate the electrical field produced by the point charge in terms of the Coulomb's law, then use the so-called superposition law. We sum up all the electrical field produced by many point charges based on the geometry to find out the total electrical field produced by this infinitely long line charge. In this case, we will treat this problem from another perspective, that is using the Gauss's law for the electrical field. That is the volume integral of electrical charge density equals to the closed surface integral of electrical flux. So say we have infinitely long line charge distribution. 注意这边的电荷，这个不是电流这是一条无限长的带电荷线，不是带电流线所以它上面的是电荷密度 low 所以你看到的应该是 low 零low L 零line charge. And for this case, we draw an imaginary cylinder enclosing this line. Which has a length of L, a radius of R, and this cylinder is placed symmetrically along the z-axis. So what can we do is try to calculate the electrical flux, the surface integral of electrical flux along this region. So for this cylindrical region, using the Gauss's law for the electrical field. The right-hand side is relatively simple, which is the total electrical charge enclosing within this within the cylinder. So the total charge will be the line charge density rho sub L0 times the length of the cylinder L. So that's the right-hand side of the equation. How about the left-hand side? Left-hand side, as you can see here, is the closed surface integral of this cylindrical structure. How many surfaces is there on this cylindrical structure? Well, we have 3 surfaces: the top, bottom, and the side. The side is a cylindrical surface. The top is a planar circular surface, and the bottom is a planar circular surface as well. So to calculate the closed surface integral, in theory, you will proceed the surface integral for 3 times on top, bottom, and the side. However, because of your prior knowledge about the electrical field distribution, that is, for this infinitely long charge wire, the electrical field goes out of this line in a symmetrical fashion. That is, the electrical field, E, only appears on the ER direction. 所以讲吼，咱家嘛是加减啊偷食报啦吼。所以我们知道，在这一个几何的分布条件底下，这一个无限长电荷线的电场，它是均匀辐射出去的哈，往外沿着 R 方向辐射出去。所以这个的结果是什么？这个的结果导致于对于这一个柱状的那个封闭面，其实我们只需要算侧面就好，上面跟下面不用算。为什么？Because on the top surface you shall account for easy component. The bottom surface you need to account for easy component as well. And from the geometry of this problem, you don't have easy component. You have 0 easy component. Sorry. You have 0 easy component and 0 phi component as well. So you need to only account for the electrical field passing through the side. All right? So the surface integral of the left of this Maxwell Gauss's law for the electrical field is reduced from a closed surface integral to just the cylindrical side. Okay? So here we write up the expression for surface for this cylindrical surface. That is, this is ds for the cylindrical surface. So you have r d phi dz ar. So the direction of the surface is ar direction. And you have differential length in the z direction, and you have differential length in the phi direction. Note that in the phi direction, d phi is not a length, it's only a degree, difference in degree. So you need to multiply by r, so to give a differential length in the phi direction. So for the surface integral expression on the cylindrical surface, you have r d phi dz ar. And the integrand that seems to be integrated is the r component of d. So you write as dr as a function of r, ar. And of course, so far you don't know the dependence about dr. So you leave it as a function, say dr as a function of r. Note that for the integral, for the two integral in the phi direction and z direction, the function to be integrated, that is dr as a function of r, has no dependence on phi and z. So the integration can be performed relatively easily. So you don't, because dr involves no phi nor z dependence. So you can carry out the integration as 2 pi r L, 2 pi r L times dr as a function of r. Then you can put up the left-hand side and the right-hand side together. So you end up with dr as a function of r equals to rho sub L0 divided by 2 pi r. So here we correctly predict that dr is a function of r, which is inversely proportional to the distance r. And recall the result of example in section 1.5. The electrical field intensity produced by an infinitely long line charge is rho sub L0 divided by 2 pi r epsilon. Epsilon is the permittivity. So recall the relationship between D and E. You can get the same result by dividing this with the permittivity epsilon. Okay? So this is the same result as we have seen in section 1.5, where the calculation is relatively simple. All right? Okay, so let's break for 5 minutes, and then we continue for example 2.7.